All right, we're going to finish our conversation about electron configurations and talking about valence electrons and some periodic trends. So valence electrons are the outermost electrons. They have the highest energy levels. And they're important because they're on the outside. They really are they're the ones that really determine how the element, the atom, the particle is going to behave. These core electrons that are close to the nucleus are not going to do much moving around or being transferred, but it's the ones on the outside that are going to be interacting with other atoms, other ions, etc. So think about it like when you put on whatever you put onto the outside world as kind of your valence, and then your core is like who you are, you don't really show that to the rest of the world. So your valence electrons are kind of like whatever you put on for the outside is how people are going to perceive and interact with you, this outer self. So the valence electrons can be found by looking at the electron configuration and deciding what are your highest energies. So for silicon, for example, I have energy levels of 1, 2, and 3. The highest of those is 3. So how many valence electrons do I find in energy level 3? Well, I find 2 in the 3s and 2 in the 3p. So this gives me a total of 4 valence electrons. So silicon has 4 electrons on the outside ready to interact with other atoms. If you have an element that goes through the D block, because the D block goes down in energy, your outer is only going to be that highest energy level. So, and this definition will possibly differ once you move on to higher levels of chemistry. But for this course, we really want you only looking at that highest energy level for your valence. And it depends on, that's just kind of how this textbook is pulling that together. But it depends on your instructor if you're going to include all of these as valence, or if you're only going to include the highest energy as valence. For my class, I will keep it simple and follow the textbook and say the highest energy is going to be my valence. But for some instructors, it's anything outside of that noble gas configuration that's going to be considered as valence. So pay attention to the way that your instructor wants you to identify these things. But for this, we're looking at these 6 valence electrons because there are 2 in the 4s and 2 and 4 in the 4p, so there are 6 total, and then the rest of these are going to be core. So you can write out the electron configuration and show the valence that way. Another way to kind of cheat your way through valence is to look at the group. So if you look at the electron configuration of the last, the valence shell essentially, see how these have 1 valence in group 1? These all have 2 valence in group 2, and then notice we skipped the valley, we skipped the transition metal, so we're moving all the way over here to boron and aluminum, which are group 3a, and look at, they have 3 valence. Then we have 4 valence, 5, 6, 7, 8 valence. So the tall groups, your representative elements, their group number tells you the valence, except for my little friend helium, which is an exception, only has 2 valence, doesn't have 8. This 8 valence electrons, this is so crucial. That is what everyone wants, because everyone wants to be like a noble gas. We all want to have those 8 valence electrons, something called the Octet Rule. That means that we're going to act in a way to get us 8 valence electrons as fast as possible. So when we talk about bonding later, that will be a big influence in how things behave. So because of these electron configurations and what electrons, what these valence electrons mean, and the way the atoms are set up, we can decide or we can predict behaviors based on where you are in the periodic table. So you already know about families, and families can behave similarly. Now we kind of know why families behave similarly. It's because if you're in the same family, you have the same valence electrons as everyone else in your family. So you will behave similarly to get your 8, you get your octet to look like that noble gas. What I want to highlight for you here, or pull out for you here, is 2 elements. We're going to pick fluorine over on the top right and francium over on the bottom left. And we're going to analyze fluorine and francium for these periodic trends. I'm leaving out the noble gases because they don't interact with other elements very often. So they're kind of a separate category. So here are the trends that we're going to talk about. The definitions first. You need to know what the trends are before you can tell me, what's increasing or decreasing in a certain way. So the atomic radius is the distance between the nucleus and the valence electrons. So it's just like a circle radius. The center of your atom just happens to be the nucleus. And the outermost electron is an electron, and this is your radius, just like the radius of a circle. Your ionization energy is the energy required to remove an electron. So you want to take an electron from an atom. How much energy do you have to put in to remove an electron? Things cannot just lose electrons because you have a positive nucleus and a negative electron. There's an attraction here. So how much energy is required to pull this electron away from the nucleus is what ionization energy is. Electronegativity is how much an atom pulls other atoms' electrons. So if it's how much I pull, so if this is my nucleus, it's how much I pull your electron if we're in a bond. So that's would be the electronegativity. And then electron affinity is much more complicated than this, which you'll learn about later on in your chemistry career. But for us, for right now, it's just going to be how much an atom attracts electrons, how much does it want an electron. So electron affinity is that. But I'm really going to focus on these 3 for any quizzes or exams. So in order to figure out what these trends are, you can absolutely look at a periodic table. Your textbook is going to tell you, okay, we're increasing one way, we're decreasing another way on the periodic table, across, down. If you know me, I get confused with up and down and left and right. So I like to have a story. So we're going to think about these 2 elements. Francium, which is in the bottom left, and fluorine, which is on the top right. It's not the farthest top right, but it's pretty close. So we have these 2 F's, francium and fluorine. So let's take a look at our periodic table and let's analyze what's going on with our francium and our fluorine. Actually, I'm just going to redraw this down here. So we have our francium hanging out in the bottom left, and we have our fluorine hanging out at the top right. What happens to my radius? My atomic radius, which is my size, as I move down the periodic table toward francium. Well, think about what happens as you move down the periodic table. Let's start with our hydrogen. We have 1 ring. Think about that Bohr model. Then we have 2 rings. Then we have 3 rings. What's happening to my atomic radius? Then I have 4 rings. All the way down, keep going, to 7 rings, right? Which is very large. Let me see if I can fit 7 rings in here. 1, 2, 3, not working for me. 5, 6, 7. Okay, sure. Now, the rings actually get smaller as you go out. I'm not drawing a very good picture of this, but you get the idea. Build a snowman. Do you see the snowman? Build a snowman. This is your moving downwards. Okay, build your snowman. And then, So we're increasing going down. Francium is big, has 7 rings. So we're getting bigger as we go down. Now we're going to take our snowman, which is really nice and cute, and we're going to knock him over. So we're going to knock the snowman over. It's very sad. Our snowman is very sad with us that we knocked him over. Which means that moving toward the right, we're getting smaller, so we're decreasing. Why is that? That's kind of interesting, right? Let's look at lithium versus fluorine. Let's just take 2 out and just look at them. Lithium has, look at your periodic table and tell me, lithium has how many protons? So lithium has 3 positives in the nucleus, and my electrons are 3 electrons hanging out outside. And that's not exactly the way that it looks, but we're just kind of look at that. Versus fluorine has 9 protons and 9 electrons. But they're pretty much the same energy levels, right? They're both on the second energy, so 2 rings. It should seem, I should draw this correctly, which is smaller. It should seem that fluorine should be bigger because it has more stuff in it, right? But can you think of a reason why fluorine would be smaller given this information? Fluorine is smaller because it has a greater attraction. This all has to do with attraction. It's something called Coulomb's law. 9 pluses and 9 minuses has a greater attraction than 3 pluses and 3 minuses. So the greater your attraction, the closer you hold your electrons. So fluorine is holding its electrons really tightly because it has a greater attraction to them, which makes it smaller. This is really key. Thinking about this is key because it helps us with the other trends. If you're confused about anything, take a picture of this and then text me. So our next trend is going to be ionization energy, and this is based on the same ideas. It's the energy required to remove an electron. So we're going to look at, as I go down towards francium and as I go across towards fluorine, how easy is it to take an electron? The electron is hanging out right here. So let's say the electron is hanging out down here and the positive's all the way in the middle. It's pretty easy to take away this electron because it's so far from the nucleus, right? It's like if I leave my laptop in the lobby of my apartment building, it's going to get stolen from me because it's far away from me. My electron is really far away. Even though I'm attracted to it, it's still too far for me to really hold. So we have a decreasing energy, which means it's easier. So decreasing here means it's easier to take electrons from francium. It's easier to take the electron from francium. Versus fluorine, we just said, hey, fluorine has a greater attraction, right? Because it's small size. So we have an increasing energy because if I'm holding my laptop really close to me, then it's harder to take away. It's harder to take electrons from fluorine. It's really, really hard to take electrons from fluorine. And then electronegativity is really based on size. How small you are depends on how well you can pull another person's electrons depends on how small you are. So because francium is so big, it can barely hold its own electrons, let alone pull somebody else's. It's too big to get its nucleus, to get positive nucleus close to other atoms' electrons, versus my little friend fluorine is small. So it can get close to other atoms' electrons and pull them. And again, it's that nucleus that's really getting in there. So we have increasing going towards fluorine and decreasing going down towards francium. And then for your electron affinity, I'm just going to refer you back to the periodic table. How close you are to a noble gas tells your affinity. If you're in group 7, you have a high affinity because you really want an electron to become a noble gas. If you're a nonmetal, though, you have a low affinity because you actually would like to lose an electron to go back to becoming a noble gas, right? So that's electron affinity for you. So hopefully that was helpful. I'll come back on this slide and let you look one more time at that last piece. And let me know if you have any questions.